So we're going over Chem 113 Exam 3. Starting with question 1, we're asked to draw a mechanism for the following reaction. So in this case, we have this beta keto ester relative, except rather than an ester, we have a lactone. We treat it with aqueous acidic conditions. So it looks like we're going to hydrolyze this lactone and then from there decarboxylate. So in our first step, we're going to protonate our lactone carbonyl. From here, it's now activated for attack with nucleophiles. In this case, water can attack and open up to generate a tetrahedral intermediate. Now, from here, we're going to have to activate the alcohol as a leaving group. We're still under acidic conditions, so we can't have anions just floating around in solution. So in order to activate our lactone oxygen as a leaving group, we're going to protonate that oxygen. And we're going to deprotonate and free up a lone pair on our water equivalent. That in turn gives us the following tetrahedral intermediate, which can then collapse via 1,2 elimination pathway to give us our free carboxylic acid. Now, although this is an equilibrium process, this next step is going to drive the equilibrium to completion. So our adjacent beta carbonyl will pull off a proton. We will form a carbon-oxygen double bond, and we will break our carbon-carbon bond. And this is really important because I saw a lot of the times on the exam, students forgot to draw the corresponding enol generated. This is important because in order for the next cyclization step to occur, we're going to need to convert this enol tautomer into the corresponding keto tautomer. So we're going to abstract a proton and then protonate the relatively electron-rich alpha position. So now we have our alcohol ready to go. And now we have a textbook acid catalyzed nucleophilic addition. We've seen this in previous reactions of carbonyls where under acidic conditions, we can generate, in this case, a hemiketal. We're going to protonate our ketone. That activates the ketone carbonyl. And we still have a lot of stereochemical information here. This alcohol is on the top face, so it will attack and will generate a cyclic product. Now, I noticed in some cases that students forgot to show the deprotonation step. Just redrawing that methyl group in that we didn't lose in this process. They forgot to show this deprotonation step just to get a neutral isolable final product. From here, that gives us our drawn product. So this is a combination of the hydrolysis, decarboxylation, and hemiketal formation mechanisms that we've seen throughout this class. Any questions on this example? Okay, let's keep going. So the following aldol condensation yields a single product after dehydration. Predict the major and minor product. Draw the structure of the major and minor product from the first step before dehydration. Draw a mechanism for each step. During the dehydration step, show how the minor product can be converted to the major product. Okay, so let's start first and foremost with just a basic mechanism here. So when it comes to enolate formation, we know that LDA has a strong preference to generate kinetic enolates if you use one equivalent of LDA. So we're going to pull off a proton from the least hindered alpha position. Enolate generation in this case is irreversible. From here, I'm just going to redraw the enolate to make it easier to show this next addition step. Our enolate is nucleophilic. We have an electrophilic aldehyde. So our enolate will attack the electrophilic aldehyde and generate an alkoxide product. Now from here, I'm going to call this substrate. I'll abbreviate this as subs. So likely what happens in order to quench out this alkoxide, it's probably going to pull off a proton from an equivalent of substrate. And that gives us a isolable, though not particularly stable, beta hydroxy ketone. Okay, so this is our major. And we'll see why this product is major when you think about the aldol reaction and what drives the aldol reaction. Before the dehydration step, the aldol reaction is reversible. So once we have this major product, you can, and it's reasonable to show under basic conditions, the dehydration step occurring. It's not super common to see spontaneous dehydration under basic conditions without heat, but it's not unreasonable to propose. Usually this beta hydroxy ketone is driven to completion and we convert this beta hydroxy ketone to the enone to drive this aldol to completion during a separate dehydration step, be it during the quench or as a separate entire step. So when we treat with H3O+, we're going to protonate and activate our alcohol as a leaving group. From here, now that we have this activated leaving group, you can show this as a 1,4 elimination or as an E2-like mechanism. An E1-like mechanism is not acceptable in this case just because your carbocation wouldn't be particularly stable. So that gives us our aldol dehydration product, which we get as a major product. This is our major product after dehydration. And this is the easiest to isolate because typically, due to the fact that the aldol reaction is reversible, especially for more hindered aldehydes, you run into issues cleanly isolating this beta hydroxy ketone without a substantial amount of retroaldol. So to get reasonable yields, we usually do the dehydration step immediately after. Does this major product reaction sequence make sense? Does this reaction sequence so far make sense? Any questions so far? Okay, let's look at the minor process. I know a lot of students were making arguments based on strain, And that's not entirely correct in this case because there's a more glaring issue that needs to be addressed. So if we look at the minor pathway, which would involve reaction of our other alpha position, we make our enolate. And this enolate you can easily generate under equilibrating conditions. This is in fact a thermodynamic enolate. And this enolate can certainly react with electrophiles such as this aldehyde. However, in addition to being strained, there's an even bigger issue when you take a look at this initial aldol product. What is a mild issue with this aldol product if we wanted to drive this reaction to completion? Not only are we generating a pretty hindered stereocenter, that's one consideration, but also if we want to drive this reaction to completion via dehydration, there's no available hydrogen to abstract. So this substrate cannot dehydrate, or at least not easily. So this beta hydroxy ketone product is not going to be particularly easy to isolate. You're going to see a lot more of the major product compared to this minor aldol product. And that's simply because this aldol reaction is reversible up until the dehydration step. You see equilibration between the major and minor product in most cases. And because you see this equilibration, you can end up with funneling towards the major beta hydroxyketone product and even funneling to the major dehydration product during the dehydration step. And that's why I had you draw out the mechanism to show how this minor product converts to the major dehydration product. So let's show that now. So if we have our minor product and we think, great, I'm going to take this compound and I'm going to try and subject it to dehydration conditions. What will I see? What will happen? Well, first, there's going to be a protonation of our ketone. From here now, we're working under acidic conditions, and we know that the aldol reaction is an equilibrium reaction. There's equilibration, and the key driving step is the dehydration. So under acidic conditions, we can easily initiate a retroaldol, and that in turn generates an enol tautomer. From here, we can tautomerize this enol tautomer. So now that we have this ketone, what we can do is we can tautomerize our ketone. So now we're generating the other enol tautomer. And this is all an equilibrium process. So from here, let me redraw this enol tautomer. Now that we have this enol tautomer, let me redraw it just so the drawing's a little bit cleaner. There we go. Okay, so now that we have this enol tautomer, it can react with activated electrophiles, such as our protonated aldehyde, to generate aldol products. And the reason why we see funneling to the major product has to do with the fact that this dehydration step, this very important dehydration step, can actually occur for this substrate. Okay, so we're going to do some proton transfers. So we're going to deprotonate the ketone. So here now we have our beta hydroxy ketone that matches the major beta hydroxy ketone observed. Now to drive this equilibrium towards the product side, we're going to protonate. We've now activated our alcohol as a leaving group. And from here, water can abstract a proton. We eliminate, and that gives us our desired aldol dehydration product. So this shows how even the minor beta hydroxy ketone obtained can be converted into the major dehydration product. Does this make sense to everyone? Does this explanation make sense? So it's not a matter of strain. For the minor product, the dehydration step physically cannot occur. Any questions before we move on from this example? Okay, so in this case now we're asked to propose a synthesis of the following molecules from compounds containing 6 carbons or less. These substrates are designed in a way where only a few of our synthetic methods would work efficiently. So I'm going to choose to break this carbon-oxygen bond to trace this back to an acyl chloride and a highly hindered alcohol. The reason why we have to utilize the acyl chloride method stems from the fact that because our alcohol is tertiary and hindered, we can't use the carboxylate method because an SN2 in a tertiary center is not particularly viable, nor can we use Fischer esterification because we'd likely see elimination before any productive esterification. So that's why we're forced to go through the acyl chloride, because the conditions are mild enough to install even hindered alcohols. Does this discussion make sense to everyone? So for example, if you proposed using the carboxylate method, this runs into some issues. You'd likely see E2 rather than the desired substitution reaction. You can't have a substitution reaction, at least in an SN2 format, on a tertiary center. And by the same token, if you try to do a Fischer esterification with sulfuric acid or any strong acid, for example, you'd likely see E1. You'd see more elimination than productive esterification. And that's why these two routes are not viable. Does that explanation make sense? Any questions on this example? Okay, if we don't have any other questions, let's look at the next. So in this case, we're asked to propose a synthesis of the following molecule from compounds containing 5 carbons or less. Again, I'm probably just going to break this bond and go through the acyl chloride. Let's talk about some of the less viable routes. Let's talk about some of the less viable routes. I have some students proposing the carboxylate route. It's not entirely unreasonable, but that's a very hard reaction to get to occur practically. Mainly because although this is a primary alkyl halide, it's a very hindered halide. Thankfully, this substrate can't undergo elimination, so the carboxylate method's not unreasonable, it's just not the best. You'd see substantial side reactions. By the same token, I have a lot of students who proposed a Fischer esterification, and again, that's a little tricky, mainly just because although this is a primary center, any ionization you can see shifts, and you'd also be hard pressed to get this really hindered nucleophile to react efficiently in the Fischer esterification. But both of those are reasonable to propose just due to the unique nature of this substrate. Personally, I would go through the acyl chloride as it's the most tolerant of these hindered nucleophiles. Does this discussion make sense? Any questions before we move on? Okay, let's try to now look at the next problem. We're asked to draw a mechanism for the following reaction. So in this case, we have a carboxylic acid, and we're treating it with phosphorus tribromide and bromine. These are classic Helvold-Zielinski reaction conditions. So our first step is our nucleophile, which is our carboxylic acid oxygen, will attack our electrophilic phosphorus atom. That in turn gives us an activated alcohol equivalent as our leaving group. And we've also activated our carbonyl carbon for reaction with even weak nucleophiles such as bromide. Bromide will attack the electrophilic carbonyl carbon, and we will generate a tetrahedral intermediate, as we've seen time and time again. From here, we're going to kick out our activated leaving group, one of the few cases where bromide is not the best leaving group of our choices, and we'll generate our protonated acyl bromide. From here, we can deprotonate our alpha position, and bromide is the most reasonable base in this case, because if we had water floating around, we would be back to square one pretty quickly. It's always important when you're drawing out the acid and base from any reactions, even proton transfer reactions, that you think about whether it's plausible for that species to exist under the reaction conditions. So we deprotonate the alpha position, tautomerize this keto tautomer to the enol tautomer, and that enol tautomer is sufficiently nucleophilic to react with electrophiles such as bromine. From here, that in turn is just going to generate our alpha brominated acyl bromide, which can then be deprotonated to yield our alpha bromo acyl bromide. From here now, as I mentioned in class, we can quench the acyl bromide with a range of nucleophiles to give a range of carboxylic acid derivatives. So if we quench with methanol, we're going to get a methyl ester, right? Methanol will attack our electrophilic carbonyl carbon. From here, we generate a tetrahedral intermediate. And it wouldn't really be appropriate to show water facilitating the proton transfer. Likely, we're going to have an equivalent of methanol facilitating this proton transfer. Okay, we've now set up our tetrahedral intermediate to collapse and kick out our leaving group, which in this case is bromide. And that gives us our desired alpha bromo acyl bromide. Sorry, alpha bromo methyl ester now. We've in effect converted this alpha bromo acyl bromide during our quench into an alpha bromo methyl ester. Does this proposed mechanism make sense? Okay, so let's keep going. So in this case, we're asked to propose a synthesis of the following molecule from compounds containing 5 carbons or less. And there are a few very odd responses. So let's talk a little bit about some pattern recognition here. Anytime you see these methyl esters, it's important to think about disconnections surrounding the alpha position. So to help everyone see what I mean, I'm going to propose a functional group interconversion, where we trace back this methyl ester into like a malonic ester derivative. From here, it's easy to see how if we break these two bonds, that gets us to a malonic ester, which is going to be our nucleophile, and this dibromide electrophile. And because our malonic ester is symmetrical, that gives us a little bit of control in this dialkylation. Remember, dialkylation of malonic esters with dialkyl halide, with for example, dibromo dichloro or diiodo alkanes is a wonderful method to prepare even small ring sizes. So with this proposed synthetic scheme, we have our retrosynthesis sketched out. We're now going to propose our forward synthesis. So we're going to start with this malonic ester variant. We're going to treat it with sodium methoxide, followed by our dialkyl halide. If you wanted to minimize the chances of side reactions, you could do LDA in excess or any other non-nucleophilic base in excess, though usually you'd see proton transfer before any elimination or substitution side reactions. Anyway, so in this case, what we're seeing mechanistically is that we're deprotonating our alpha position. From here, the malonic ester derived enolate will serve as our nucleophile, and it will attack our electrophilic carbon of our dihalide. That in turn generates our alkylated product. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. From here, let me just redraw this a little bit. we're going to again successively deprotonate our alpha position to generate another enolate. Do we have to show the mechanism for this? No, we don't. Okay, so I was thinking of the previous problem. Anyway, so let's just draw out this dialkylation product. And then from here, first we're going to treat with H3O plus and heat to decarboxylate. And then we treat with HCl and methanol to reinstall our methyl ester. Remember, the decarboxylation step converts these methyl esters into carboxylic acids. So we have to regenerate our methyl ester via Fischer esterification. Does this synthetic sequence and does this idea of pattern recognition in synthesis make sense? We can recognize this 5-membered ring attached to a methyl ester as a dialkylation of a malonic ester. Any other questions on this example? Okay, let's keep going. So in this case, we're asked to propose a synthesis of the following compound from the indicated starting material. And again, I saw a few somewhat odd proposals. Let's talk through some main features of this substrate, and let's talk about some things that we need to consider. First, we have this highly congested center. And this is problematic because it limits what kind of bases and conditions we can use. If we have strong nucleophilic solvents or strongly nucleophilic species such as methoxide floating around in solution, we can easily initiate retroclason reactions. So the first thing I'm going to do from a retrosynthetic perspective is I'm going to lob off these two identical alkyl groups. Because I notice that if I do that, I start to get structures that closely resemble our starting material. So once we've lobbed off these methyl groups, we notice that if we break this bond, we immediately get back to a Claisen reaction between two equivalents of our starting material. This is the key pattern recognition needed to propose an efficient synthesis of this compound. From here, we're now going to draw out the forward reaction. So we'll take this methyl ester and treat it with sodium methoxide. From there, that will deprotonate our alpha position. I know some students have proposed a mixed Claisen using LDA to irreversibly generate the enolate. But considering the small pKa difference between the two substrates, it'll be pretty difficult to avoid some side proton transfer reactions. Regardless, this entire Claisen reaction is reversible up until the final step. So we deprotonate our alpha position. Our enolate will then attack our electrophilic carbonyl carbon, and we generate a tetrahedral intermediate. Okay, from here, this tetrahedral intermediate will collapse and will kick out methoxide. Okay, now this is really important because many of the synthetic routes that I saw did not account for this last Very important, very critical step. So when we have this beta ketoester formed from the Claisen reaction, what drives the Claisen reaction to completion? What ensures a product-favored Claisen reaction? The deprotonation step, exactly right. So in order for this reaction to be product favored, at the end of our Claisen reaction, after we form the beta ketoester, we're going to deprotonate our beta ketoester. This enolate derivative is resistant to attack from nucleophiles and cannot undergo retroclaison. So after a quench, we will have our desired beta ketoester. So what can we do with this beta ketoester from here? Well, we're going to have to sequentially methylate it. And in this case, I would probably recommend using two different bases. The first case, you can do sodium methoxide. I personally would use a non-nucleophilic base, such as tert-butoxide, and then methyl iodide as our electrophile, just to minimize any chances of undesired retroclaison happening after alkylation. And then for the second step, we'll have to use a stronger base to alkylate our second position. So to draw out the mechanism for that, if we have our beta ketoester and we treat it with methoxide, we'll be able to generate our enolate. And then from there, it can react with methyl iodide via an SN2 reaction. Chloromethane, it's okay, but generally methyl iodide is used for these alkylation reactions because iodine is such a substantially better leaving group. To show the mechanism for the second alkylation step, LDA is going to deprotonate our slightly less acidic alpha position. It's important that you avoid using a strongly nucleophilic base because you're going to end up in a situation where retroclaison can occur. So that's why we use LDA. It's a non-nucleophilic hindered base, and that allows us to methylate our alpha position cleanly. If we just dumped in an excess of methoxide and excess of methyl iodide, we'd likely see some retroclaison products. Does this mechanism and does this reaction scheme make sense? Any questions on this example? Okay. So let's look at this next example. In this case, we're asked to draw a mechanism for the following reaction. So we have a diketone and an enone. These are textbook conditions for a Robinson-like annulation. So in this case, our base, which is sodium hydroxide, is going to pull off our highly acidic alpha proton. From here, once we have our enolate is nucleophilic, and it can attack electrophiles, such as the beta position of our enone, to generate a new enolate. From here, this enolate will undergo protonation and deprotonation to generate a enolate that can react productively via an aldol reaction. So we're going to pull off the relatively unhindered alpha proton. We generate our enolate, and this enolate can attack one of our electrophilic ketones in order to generate the following beta hydroxy ketone. From here, you can isolate the beta hydroxy ketone, though usually it's converted via heating or, in this case, under acidic conditions, to the corresponding enone. Under acidic conditions with paratoluene sulfonic acid and water, we're going to protonate our beta hydroxy group. We've now activated it as a leaving group. And then from here, we will eliminate an equivalent of water to generate our desired enone. Does this mechanism make sense to everyone? This reaction actually works best when we have an R group at this position. Yeah, you could see some of the other enone product, though the bridgehead hydrogens are a little bit harder to remove, and there are more limitations in terms of what arrangements would give a productive E2 reaction. Did that answer your question? Okay, let's keep going then. So in this case, we're asked to predict the product from the reaction and draw a mechanism. So we're treating a methyl ketone with bromine and sodium hydroxide in excess. So this is the textbook haloform reaction. So we're going to see essentially the same step repeated 3 times. We're going to deprotonate. From here, now that we have an enolate, that enolate will attack our electrophile, which in this case is bromine. And we're going to generate our alpha bromo ketone. We are then going to repeat these steps of deprotonation and bromination a total of 3 times. The reason why this reaction works so well is after the first bromination, we have in effect activated our alpha position, made it more acidic, and thus easier to deprotonate, and thus easier to brominate. So a second bromination step gives us our alpha dibromoketone. We'll see yet another deprotonation step to make another enolate. And we'll brominate that enolate. And now we have the key step for the haloform reaction. We now have this reasonable leaving group in the form of the haloform anion. So our nucleophile can attack. We generate a tetrahedral intermediate. And this time we can kick out our leaving group, which is an equivalent of haloform anion. And as the key final step that drives this reaction to completion, our equivalent of haloform anion is going to deprotonate our carboxylic acid. And that in turn gives us our carboxylate salt that during the quench step gets reconverted back to the carboxylic acid. Does this mechanism make sense? Okay. So now we're doing some product prediction. So if we treat an alpha bromoketone with pyridine or any non-nucleophilic base and heat, we're going to see a textbook E2 reaction. And in this case, since we have 2 options for what proton we can abstract, we'll prefer to eliminate to get the transalkene. The second case, we treat an acyl chloride with lithium dimethyl cuprate. As we know, organocuprates are unique in that they prefer monoaddition into acyl chlorides. So we're going to see attack of our alkyl cuprate. We're going to generate a tetrahedral intermediate, which will then immediately collapse in order to generate the following alkyl copper species. Reductive elimination gives our desired methyl ketone and an alkyl copper species. So not the most atom efficient method, but certainly quite a unique reaction. Any questions on this example? So with that, we've completed our overview of Chem 113 Exam 3. Any questions? So we'll archive the